Today we are going to have our first session on Netlink, socket and Netfilter. There could be two more sessions, part 2 and part 3. So can you see my screen?
Yeah,
Yes.
yes.
Yes, it's visible.
We can see your screen.
So in today's session, we will mainly discuss with the Netlink, although not the Netlink fully, because that will not, we may not have the sufficient time to fully cover the Netlink by today. Let us see how far we can move ahead. So initially we will talk about the inter-process communication, why Netlink has come, what is the difference between Netlink and the ICTL. Then a brief idea on the Linux network stack, because finally it is all about the networking and Linux kernel internal networking. So we must have a brief idea, if not the detailed idea, about the Linux networking stack. And then we will start the basic functionalities and APIs of the Netlink socket. Later on in next session, we will have more detail about the Netlink, how it is working and so on and so forth. Then some examples, some dummy code and all that. So during the session, if you have any question, please interrupt me at that point of time. No need to wait for the end of the session, because there is no such question and answer session at the end of this. So if you have any questions at any point of time, feel free to ask me. So let us start. Okay. So this is all about. Okay. So Netlink is basically an inter-process communication. So before going into details of Netlink, let us see what is IPC or inter-process communication and why inter-process communication is required. In our standard operating system like Linux, Windows and all, they have mainly two parts. One is the Linux kernel or the kernel, and the other is the user space program. Now, why we separate these two? There are multiple reasons for that. One of the reason is that from the developer point of view or from development point of view, is that developing anything in the kernel, implementation, anything in the kernel require a detailed level of knowledge, and it is pretty much complex. The outcome of this could be severe. Means if it is your user space application, and sometimes it may have some segmentation fault due to improper design or incorrect implementation, the side effect of this is very small compared to you have modified something in the kernel, and for the same reason you have some segmentation fault kind of error in the kernel, then the outcome is very severe. Your board could be, or your laptop or your machine could be restarted. Sometimes it could be damaged. It may not be restarted. Damage in the sense not the hardware damage, but the operating system could be corrupted, and so on and so forth. So it is always better to not to work in the kernel unless and until it is absolutely necessary. The second is as a result, the core functionalities of the operating system, for example, memory management, scheduling, interrupt controller, interrupt management, although the network functionalities are not the basic core functionalities of any operating system, but uh, it is an integrated part of operating system. So we can think of this as a part of operating system. So those are the things which comes along with the operating system or kernel. And also there could be some feature which requires very much performance critical part. It's a real time data need to be sent or received or need to be analyzed and all that. So if your program or your work is very much performance critical, then sometimes those are also placed in the kernel. Otherwise, the remaining part are usually located in the user space process or the user space application. For example, your GUI, your audio system, your offices kind of applications, all are running on the user space program. So in summary, we have two kind of address space. One is the user space applications and the other is the kernel space or system space, whatever you call it. And very frequently, may not be always, but very frequently, it is required to communicate from user space application to the kernel space module or kernel space, any core functionalities. For example, you want to know the IP address of a particular interface. You want to know the route table of your board or your PC or your laptop. You want to know the ARP entries currently available. What is the firewall rule? There are many functionalities that user space program or applications need to know during its while it is running on the system. So for that, communication between user space application and kernel space are very common. By the way, inter-process communication is not limited between user space application and kernel space code. Two user space can communicate with each other using, say, socket or pipe or signal. Those are also considered as inter-process communication. Also, two physically separated machine can communicate with each other, like you are accessing the google.com, like we are currently communicating with each other in this session. These are also considered as inter-process communication. One process in my laptop is communicating with a particular application in your machine. So those kind of application, Netlink is not there. Netlink is not for those kind of application. Netlink is only required or only used when user space application needs to communicate with the kernel space or two kernel module need to communicate with each other. Those are the only cases where Netlink socket can be used. Netlink socket cannot be used to send a message across a machine. For that, other BSD sockets are already there, TCP socket or UDP socket and all that. Now, through user space, as I said, the user space application can communicate with kernel space program through multiple available already supported system. For example, IOCTL. IOCTL is one of the way through which user space application can communicate with kernel, it has some limitation. That is why Netlink comes into this picture to overcome those limitations. There are system calls through which you can communicate with the kernel also. There are proc file system, which is very famous. We actually had a session on the proc file system also. So the proc file system is one of the mechanism or method through which user space application can communicate with the kernel space. And there is obviously Netlink. As I said, they are widely used and famous IPCs. Again, these are with respect to the communication between user space application and the kernel space, not between two user space applications or between two physically separated machines. For that, we have signal, pipe, socket, shared memory, FIFO, named FIFO, and all that. You possibly all know about those. So any questions so far? I think this is very introductory session, so I'm not expecting any questions so far. Now let us see why the Netlink socket comes into this picture. This is basically developed to overcome some limitations of the IOCTL. So to understand the limitation of the IOCTL, let us have a brief idea of what IOCTL is capable of and how it does. User space application can set or get some information from to and from the kernel using IOCTL. For example, very common tools that we used in Linux system are the net tools. For example, ifconfig or ifconfig, arp, route, hostname, netstat. These are the very famous or widely used applications through which you can set or get information, network specific information to and from kernel. And these are internally use IOCTL. For example, ifconfig. If you have, say, one interface in your machine, say if0, and you definitely need to configure that network interface in order to communicate with the outside world. And to do that, that interface must have the IP address, net mask, gateway address, routing entry, and all that. Those can be done using the ifconfig command and arp command, route command, and those commands, as I said, internally using IOCTL. Now the IOCTL has to have one unique IOCTL number for every single operation. For example, I want to set an IP address for my interface if0. So what I used to write the command in, I must have the super user privilege, otherwise I am not allowed to do that. So in order to do that, I usually run the command ifconfig, then space if0, then the IP address, say 192.168.1.5, and then I usually make the interface up the up. So the command is usually ifconfig if0 192.168.1.5 up. Now, if you ever check the implementation of ifconfig, it is readily available in the net. So you can see that internally it uses a IOCTL command on the if0 interface to set the IP address. Now, when you again run only ifconfig if0, it is supposed to return all the information along with the IP address, netmarks, and all of that particular interface. So for that also, internally, if config implementation calls another IOCTL, and these two IOCTL have two different unique IOCTL number. So you can imagine the number of services you are uh, using in order to communicate between the user space and the kernel space. Each one has one unique IOCTL number. But the problem here, one of the problem is the IOCTL can be invoked from the user space. So that means if you want to get some information, you have to do it using the polling method. There are two methods available. One is the interrupt method and the other is the polling method. Polling method means you are continuously asking, or you are periodically asking, or whenever you want the information, you are asking the kernel that whether you have that information or not. If the kernel has that information, you can get it. On the other hand, interrupt is something like you are doing your own job, but inform the system that if such event is happened, please inform me. So you are busy in your own work. Whenever that event occurs, kernel will inform you that this event occurs, so you can take your action. So say suppose your requirement is if there is some modification in the ARP entry, or if the IP address of the interface is getting changed, then one user's my program should be invoked. Now through IOCTL, this cannot be achieved. So if there is any change in the IP address, or there is any change in the routing table or in the ARP table, you need to poll for that information and get that information from the kernel. There is no way that kernel can asynchronously told you that this event occurs. So that is the major drawback of using IOCTL. Still in the Linux kernel, I've been using 4. Kernel also. I've noticed that IOCTL is still in use, but there is a high chance that in future these will be obsolete or just be there to support the backward compatibility, but the newer tool or newer application will definitely not use the IOCTL. It will use either the Netlink socket, or maybe if there's some advanced technique coming up on top of Netlink socket, then they will use the Netlink. They will use that. But currently, the modern, the recent tools that have been developed are all using internally the Netlink socket. I'll come to that also. So that is the one of the drawback. As I said, cannot send asynchronous message from kernel to user space. The other part is there are some, as I said, for each of the service that you want to do, you need to have one unique IOCTL number. So if you want to now have a new feature, for example, say earlier there was no way to get the IP address of the info. Please wait. So if you want to add a new feature, that means you need to add a new IOCTL number in the kernel. Now that can only be done by recompiling the kernel. And now you not only need to add a new IRCTL number, you need to add the corresponding code so that whenever user calls for some information, either to get either the IRCTL number is for getting data from the kernel or setting data to the kernel, the corresponding implementation has to be in the kernel. That means you need to add that code in the kernel. Also, in order to get it supported, you need to recompile the kernel, prepare your own image again, and boot up the device with the new kernel image. And that is always risky if you are not an experienced kernel developer. Even if you are a very experienced kernel developer, there is a high chance of very small mistake, and that could result a very severe problem in the kernel that could damage the stability of the kernel. So, as I said, modifying the kernel is not very much a recommended part of it. So, yes, this is a problem of adding new task or new feature to the IRCTL. On the other hand, as we are mentioning the disadvantages of IRCTL, that means obviously those are covered by the Netlink socket. Otherwise, we will not pointed out those mistakes here or pointed out those disadvantages here. Compared to the adding a new feature in the IRCTL, adding a new Netlink type. I will discuss about the new protocol. What is the protocol type? So adding a protocol type in the Netlink is very easy. You just need to add a new protocol number in a header file, that is netlink.h. Now you may ask that, or you may argue with me that that means also recompiling the kernel. Yes, it is, but you are just adding a new number in a header file. So the work is very trivial compared to the IRCTL, and there is no need to add any code to get the information or set the information from user to kernel. That part can be done using a separate network, separate kernel module. And having a kernel module is always better rather than compiling the kernel for adding any feature. That you must know. Do you have any query about that? That why it is why we are having an advantage if we have a kernel module for adding a new feature compared to compiling the kernel to add a new feature. I'm just pausing for 5 seconds just to check if you have any query. No, you do not. So definitely, if the asynchronous message sending is a disadvantage. Yes. Hello. Someone is muted, unmute himself or herself. Any question? Himanshu, do you have any question? You raise your hand. Hello.
No, sir.
Okay.
Not now.
Hello.
Hello.
Yeah, this is Sandeep here.
Yes.
Hello. Yeah, this is Sandeep here.
Yes. Hi, Sandeep.
Hello. Able to hear me?
Yes, I'm able to.
Yeah, we can.
Yeah, it also do the dynamic linking. Yeah, dynamic linking also possible. Right. It means like while downloading the user space application to the kernel, instead of doing it in a static stage, we can also do the dynamic linking of
What do you mean by
any
dynamic
other
linking here?
additional. It means like when I want to write
Your voice
any
is breaking.
interdimensional,
Your voice is
I can
breaking.
write
I
you
cannot hear you properly.
just now. Are you able to hear me properly?
It is audible,
Hello?
but it is breaking too much. The packet is getting lost in the network traffic.
Yeah, then it would be better. I will drop a message for you. I will drop a message.
Okay.
I will drop a message. Okay.
Yeah, please do so. Someone has asked what's the difference in these two things actually. Mayank Gupta. Okay, so if you do not know the kernel module and the kernel, then yeah, let me. It looks like some of you have some queries about that one. So yes, kernel module is a, you can think it as a separate piece of code which can work in the kernel space. That means which has all the privilege, all the access to the kernel space program, kernel space code and all that. So please wait. Hello. So yeah, the difference between kernel, built-in kernel and the kernel modules is uh, from the uh, from the privilege or the access point of view, there is no big difference. The kernel modules has all the access of the kernel space program, kernel space memory, whatever peripherals that kernel has. For example, DMA, driver, file system, networking part, and all that. So the built-in kernel code and the kernel modules has the same privilege. But the difference is if you want to, for example, you are developing a device driver. Say you are developing an USB device driver. So what you can do, you can implement the device driver and compile it along with the kernel. What it happens then, if you compile it along with the kernel, then the kernel image that you have, that will support the USB. So whenever you boot up your device, your laptop, your PC, or any embedded device with that kernel image, that will built-in support of the USB. So you can plug in your thumb drive. That, and then start. Please mute yourself. So someone please mute yourself. I cannot. There's some noise. Yeah. Thank you. So yes, but on the but the problem is, as you are compiling your code as built-in kernel, so that means if your code has any problem, that will easily corrupt the kernel. And also during the loading of the kernel, your USB module will also be called. So that means while loading the USB driver, if it has any problem, it will not allow the kernel to boot up properly. It will always crash the system. So device will never boot up. That is one problem. On the other hand, the kernel module will load after the system has boot up. So you have every chance of disabling the kernel module to be loaded if you find out that there is some problem while loading your particular device driver, the USB device driver. That is point number one. Now, assuming that you are a very smart developer, you have somehow developed the driver without any issue. So now the driver is running while boot up, but still you are using the memory. The driver code will definitely take some resources. For example, it will take some CPU resources. It will take some memory. It will communicate uh, with the other peripherals and other resources. But the board where you have loaded the kernel image, you have not plugged in any USB thumb drive. So that means the driver is not in use. There's no point of loading or having a driver unless there is any device associated with it. So isn't it better to load the driver when you plug in the USB thumb drive, do your job, and then when you again unmount or eject your thumb drive, you are now unloading the driver. That will save some resources of your system. So those are the uh, basic difference between the built-in kernel and the kernel modules. Now, from the development perspective, if you want to develop a device driver, say this particular USB driver, then to test it, you need to always recompile the kernel and load it on the system and then check whether it is working or not. And then if you find any bug during development, which is quite normal, then you need to again recompile the kernel and test it again. So that full circle of doing one round of testing of your driver will take too much time. On the other hand, you can easily compile your kernel module without recompiling the kernel and then load and unload very easily on your system and test it. So this is a third advantage. So one is the from the development point of view, the other is the usage point of view. Here also, for the IOCTL, you need to recompile the kernel to add that. That is very much risk associated with that. On the other hand, Netlink, you can do this through the kernel module. I will talk about all this. Let me complete my session. Then if you have any queries, I will do that. Yes, this kernel module is loading and unloading. You can call it as a dynamic linking or that. But usually we do not do this, do not say this in the kernel space. You can call it in the user space. Anyway. The other part is the Netlink socket support multicast. Now, what do you mean by supporting multicast? Is that suppose again we are comparing it with the IOCTL or any system call. That particular system call is used by a particular application at one point of time. So or any IOCTL. So if your ifconfig command is trying to get the IP address of your interface is 0, then it will only that particular application will get that information. So it's a kind of one-to-one communication between the user space program and the kernel space, which we can easily consider as unicast communication. But suppose there is some mechanism through which whenever any event occurs at the kernel, multiple application can be notified immediately or simultaneously. That is definitely one advantage over only getting one single application getting notified. And Netlink, by the way, support this feature. So these are the major advantage of Netlink over not only the ICTL, I have just mentioned those points with respect to ICTL, but these are the advantages over the IOCTL, the systems calls also, and the pro calls. Okay.
Hello.
Hello.
I have one question. The
Yes.
point number 4, it's written adding a protocol type in netlink.h is sufficient, right? Can you
Yes.
elaborate a little on this? The default protocols will already be there, right?
Yes.
The datagram, and TCP, and the raw. What do you mean
These are, by the way,
by
these are not those protocols. Yes. Actually, your question is right at this point of time because I have not gone through the protocol type and all that. So let me allow to go through that maybe in today's session and also in details in our next session. So then you will have a detailed understanding of the protocol type of what we are talking about, protocol type with respect to the Netlink socket. Then I believe your question will be resolved. We'll get the answer. Okay.
Thank you.
But at this moment, without knowing the Netlink socket, how it works, it is difficult for me to explain your question or answer your question. Okay.
Got it.
Tathagat, one question,
Yes.
Rahul. So when we're talking about the asynchronous, right? We are
Yes.
talking about the asynchronous from the kernel to user space events, right?
Yes.
Is there a way to when you put write some data into the kernel and when it is done, it asynchronously notified to the user? This is also mean a asynchronous from user to kernel
Yes.
space.
Yes.
Okay.
Yes. Yes.
Both sides. Okay.
So
Yeah.
so let me clarify this part for details for others. There are two ways of getting the asynchronous events. One, say you are sending the socket application, right? So you are sending some message from one machine to another. So after sending the message, you are expecting some response from the peer end or the remote end. So, but you are not continuously polling, hey, have you sent the message? Have you sent the message? You are not doing that way. You are just waiting for that. So whenever the remote end send the reply, you will get notified to the socket, to the receive call or receive message or anything, something like that, right? So that is one. Second is there is some event may occur on which user space applications are interested. You may heard about the hot plug event. So whenever in any USB thumb drive is plugged in the system, some application may invoke because it needs to mount the device and then start to access that. Maybe it's the USB network device, USB dongle. So for that, some network related application needs to run whenever a USB dongle is getting injected. So that means based on some event occurred in the kernel, some of the application may needs to be notified. So that is also you can consider as an asynchronous. Is it clear now?
Hello.
Hello.
Yeah, I'm Rohan here. I just want to
Yes.
understand. So the user space maintains a continuous channel with the kernel module where the Netlink is running.
Yes.
So so as long as the user is using that kernel module, it has to maintain the channel between the kernel and the module. Am I right?
Module means
Kernel module. The kernel
see,
space.
yeah, you do not know which kernel modules you are associated with or connected with. That is beyond your limitation. I'm talking about you as a user space program, but definitely yes, you are right. You need to get connected with the kernel. So I'm not. Let us not talk about the kernel modules. Let us talk about the kernel. So you need to be connected with the kernel. That could be either a kernel module or a kernel subsystem, something like that, that you do not know. but through socket you need to get connected with that. Otherwise, you will not get the notification.
Okay.
Okay.
I have a question.
Yes.
So we could also use Netlink socket user to for this traffic control, right? I mean,
Yes.
I've used traffic control like TC commands.
Yes.
From the
TC
user
command
space,
internally used. TC command, by the way, internally use Netlink socket.
Netlink. So, but I don't know. I was more interested in how I can use the Netlink socket to configure the
Yes,
the traffic control.
we will not cover this in today's session, but definitely we will cover that in our next session. We have a limited time, so we cannot everything by today. But yes, definitely that is one of our goals, to use Netlink in our own to fulfill our own requirement.
Okay. All right.
Hopefully, hopefully that will cover your requirement also.
Okay. All right.
Okay. So, shall I now proceed? I hope you do not have. Rohan, Nathi has just raised your hand. Do you have any question?
I have one
I
question.
asked.
Yeah, please, one by one.
Yeah. So the last point which you said.
Your
the
name is
Netlink,
very hard to pronounce. Azil Money, something like that.
It's Eril money.
Okay, sorry.
Or you can call me Ilil. Yeah, that should be
Ilil. Okay.
so fine. Yeah. So the last point which is there, the Netlink socket supports multicast. So it means like from the kernel, it is to different user space applications. Is it that way, or like
it is that way. Not from one user space application to multi. That is always can be done to use by creating multiple sockets. So that will always be unicast from user space to kernel. But from kernel to user space, so as I said, if there is some event occur, then the kernel can notify one application, or it can notify multiple applications if multiple applications are joined in that particular multicast group. So the concept is same of what we know about the unicast, multicast, and broadcast in the network perspective. The broadcast packet, multicast packet, and all that. So if you want to get the multicast packet, you need to join that multicast group. So similar concept is valid for here also.
Oh, okay. Yeah, thank you.
But in a different way.
Yeah, I understood.
Yeah. Any more question?
Hello.
Yes, right.
I just wanted to know about, are we considering any performance benefits over the IOCTL for the Netlink?
See, the IOCTL is not the performance. Okay, let me rephrase the question. What do you mean by performance? Means performance impact can be considered in many cases. So in which case you are talking about?
Okay, basically if we run any command like it tool, which uses basically IOCTL call, right? And it has the double override. Internally, it calls another IOCTL. In Netlink, we can directly set or unset the values using the Netlink socket.
Yes, but through IOCTL also you can call directly to the kernel. It tool can be it can be done in two ways. But say you are talking about if config, the ARP command, the route command, they are internally just call one IOCTL.
Yes. So is it any there are any performance improvements using the Netlink or not? That's what I wanted to understand.
See, this asynchronous part will definitely give you one advantage over the IOCTL as far as the performance is concerned.
Correct.
Because now you can do your own job. Means the performance has two parts. One is the TCP UDP performance, means the traffic that is going in and out from your machine to outside,
Correct.
whether that has any impact? Yes, no, there's no impact, neither from the IOCTL nor from the this Netlink, because
Netlink.
that will not make any impact on the traffic going between your machine and the remote machine. Okay, but these are mainly for setting and getting configuration of your system, and on top of that, Netlink is having an advantage over IOCTL is a asynchronous event. So that means the program or the user space process that you are running, it is not continuously checking whether any event is occurred or not through IOCTL call, but it can do its own job and just make a asynchronous event register to the kernel and do its own job. So whenever that event occurs, it will be notified automatically, asynchronous.
Okay, so basically we are avoiding the polling concept here.
Yes.
As we do in a IOCTL. Okay.
Yes. Yes.
Yeah. Thanks.
Okay. So let me now go to a brief idea about the Linux network stack. This is a typical Linux TCP/IP stack where there are mainly 3 layers. One is the user space, where the user space application process are running. The second is kernel space, where network stack exists. And the third is not the hardware space, I will call it, but there's a hardware. So it could be network interface card, your Wi-Fi, your Bluetooth, your USB over USB dongle, and all that. So in the net, just to get an idea, because later on we will talk about more Netlink in the kernel, how it is getting implemented and how it is getting those kind of advantage, how it is getting supported. So to know that, it is better to have a brief idea of how this network stack is working. Now in the network stack, there is a layer called system call. So whatever you are calling, say you are calling IOCTL, you are calling any socket APIs, those can be considered as a system call. So for example, you are calling IOCTL. So that means internally there's an implementation of the IOCTL like do_IOCTL, and that will be invoked. So from user space to kernel space, the system context will be done, and from IOCTL call to do IOCTL will be invoked, and that will decide whether the information need to send to the network stack or need to send to other subsystem of the kernel or not, based on some criteria. I'm not going into that. Now, as we have said, that Netlink is a socket, so that we have already known. So Netlink, definitely that means using the socket APIs, which will internally use the socket layer, but it has nothing to do with the transport layer or the network layer or the device driver, which are working underlying that network stack. Those are not related to the Netlink socket. So Netlink, for example, through Netlink socket, you can get the IP address of any interface. So that means there must be a kernel module, or I would say kernel subsystem, which is running, or which is there in the kernel space in the network stack, which is providing you the information, or which is allowing you to set the information to that particular system. Like you are setting IP address through ifconfig command. That means it will do the IOCTL. The system call will have the do IOCTL call. Then it will check the IP layer of the system, it will go through the interface and it will get the interface name that you have provided from the user space application. And then through the each interface has one net device structure there. If you do not know about the net device structure, then just assume that this is a data structure used by the kernel networking module to maintain network specific information for each of the interface. So if you have, say, 3 interface in your system, say ETH0, ETH1, and ETH2, then there must be 3 instances of net device structure in the kernel, and they are connected in a linked list. Simple, as simple as that. So now when you are calling the IOCTL, it will go through that linked list of net device list and find out the structure instance where this interface name is ETH0, and then modify the IP address of that if you are setting the IP address. Now, if you are getting the IP address, then it will get the information from that net device structure and populate your data structure so that the application get the data. Now, for the Netlink socket, this is a bit different. There must be some module. So again, going back to IOCTL. So that means this IOCTL number has to be supported by the kernel network stack. Then only, so there must be a switch case of IOCTL, number of IOCTL. So whenever, say, you are setting the IOCTL, setting the if config, setting the IP address of an interface, say the IOCTL number is 24. So whenever you are setting the IOCTL number 24, it will go through the switch cases, go to the switch case number 24, and then it will then get the IP address and populate your data structure or populate your variables. Similarly, in the Netlink socket, there must be one module which is responsible for setting or getting any that particular IP address or interface specific thing so that the application can get that. So also you are getting a, as someone was asking, so you are getting a, you are setting a dedicated connection between the socket layer and the application to the Netlink socket. And until unless that application exists, that connection will remain there. Means you are not, I'm assuming that you are not closing the socket explicitly, then the socket connection between the application and the socket layer will remain there. So if there is any data comes for which your Netlink socket is interested, then like the TCP socket or the UDP socket, that data will be queued up in the socket queue. Now, whenever the application is ready to get the data, it will get the data from the socket queue and process it accordingly. So that is again one advantage over the IOCTL. So in the IOCTL call, when you are calling the IOCTL, you are very much busy in getting the information from the kernel. You are not allowed to do anything else. You have to wait for the IO operation to be completed by the kernel, get the information, and then proceed further. But on the other hand, in the Netlink socket, you can call the API, but you can do other works also through the select call or some non-blocking socket API. You can achieve that also. So whenever kernel has the data, it will put the data in the socket queue, and like the other, as I said, like the other TCP and UDP socket, your application will also getting notified. So that means the receive message call will be returned, and then you can take the packet and do whatever you want. Okay. So again, just to summarize this slide, this Netlink socket is not dependent on the network driver. or any layer, but yes, there must be some network module corresponding to the feature that you are working on or you are interested in. Those modules has to be there. There are already by default many modules available to get the information of the netlink, and most importantly, you can add your own kernel module to have a different a new feature also. Or maybe you need to customize the TCP layer, need to have some more information based on the current status of the TCP station, or say network statistics. Those can be achieved easily by implementing your own network module or kernel module, and correspondingly a new application which is running a new netlink socket. Okay. Any question here? No, I guess. Okay. Now let us start the netlink part. So, as I said, this is a special IPC. Please note that unlike the socket is more or less a very generic IPC, which is supported by different operating system, which are means whatever, if the operating system support the POSIX subsystem, then that operating system is capable of handling the socket communication, like the TCP socket or UDP socket. But this netlink, although this is a another IPC, but this is a special IPC, and this is not supported by any other operating system. This is mainly supported by the Linux, and as I said earlier, this is not for communicating between two user space process or two process running in two physically separated machine. For those purpose, netlink socket is not your solution. Is a special IPC for transferring information between the kernel and the user space process. Now there's a catch. The catch point is this socket or this netlink can be used to communicate between two kernel modules also. There may be some requirement that two kernel module need to communicate with each other. Now the socket APIs like the TCP and UDP and all that, those are not available in the kernel space. But this netlink socket is available in the kernel space, and two kernel module can talk to each other. Now you may ask why two kernel process need to talk to each other, why there is some requirement. So let me give you one real life example. You may know about the Samba protocol or the SMB protocol. If you do not know, I'm just giving a brief idea what is it. In many cases, we remotely shared our Windows desktop or Linux desktop with our friends or colleagues, so that he or she can directly access my machine and do her own job. For that, usually SMB protocol is running in both the ends. That means, suppose you are accessing my laptop, and you are accessing my laptop in such a way that it is almost one of your drives. So you have a C drive, D drive, E drive, and whenever you click, whenever you connect to my machine using the IP address, there will be a new drive available in your system, say G drive. Now, whenever you double click on the G drive, you can access the particular set of directories of my machine, as if those directories are in your machine. Now, internally, they are actually achieving that by accessing the through assembly protocols. Now, what you are doing actually internally? So that means from whenever you are writing some, say, in your G drive, you create a new file, a.txt, and writing some data there. So, and then whenever you save that file will not save in your machine, but rather it will save in my laptop hard disk. So that means internally, whenever you are writing and saving, that means you are sending some data from your machine to my machine through network. That network will go to the user space application, and then that application will get the data. Say you are writing hi, how are you, in the notepad. So this message will come to the network application which is running in my system. It will get that message, hi, how are you, and then it will again write that data into my hard drive through the file system. So that means one context switch is happening when my network application is getting the data from kernel to user space. One context switch is there, and another context switch is happening when my application is writing the data into the hard drive from, again, user space to kernel space. So definitely you must understand that the number of times you are doing the context switch between user space and kernel space, it will have more impact on the performance. And here the performance, I mean the TCP performance, the network speed performance, that how fast you are writing that data in my machine. So I'm talking about that performance. So that will definitely have some impact on the performance. Now, to improve this performance, you may what you want to do, that whenever you are getting the data in the socket in the kernel space, you want to not, there is no point in sending the data to the application and then again coming it back to the lower layer to the kernel. Instead of that, if you can bypass the traffic from the network kernel module and the file system module of the kernel, then you can easily avoid the context switch of user space to kernel space to user space. So that means in those particular case, based on some criteria, two modules, one is network module and the other is the file system module, need to talk to each other. So this is one of the example that I can tell you where communication between two modules is required. Okay. So for that, Netlink socket is one of the solutions that kernel modules can use. The example may be a little bit complex to you. I'm not sure. I tried to make it as simple as that. But still, if you have any question about that, you can ask. In vanilla Linux, will scheduler play a major role in terms of overall latency to complete transaction? What do you mean by vanilla Linux?
I meant that it is not having any RT page or any other thing to prioritize one task over the other one.
Do you mean to say that the scheduler has no scheduling algorithm?
Let's assume that it's regular FIFO and or
Okay.
maybe round robin. So
Okay.
But let's say kernel wants to send some message to the user plane, and user plane had to do certain task based on this event. So if let's say Linux had sent a message to the user plane and it was supposed to do certain task within stipulated time, Mm, and scheduler did not invoke this thread or the process in let's say a few milliseconds. There was no I mean we do not meet our goal, so
Okay.
will there be scheduler playing major role over here?
Yes. Here in my example, it is not. But the example that you are giving, definitely scheduler has a major role to play, because there has to be means it needs to be ensured that whenever kernel is sending the data to the user space application, at that point of time, that particular user space application needs to be scheduled.
Correct.
The CPU must run that particular application. So that has to be maintained by somewhere, by either the priority scheduling or either customizing the scheduler, something like that.
Okay.
But that is the problem of Linux or any operating, or any such device, desktop operating system. So whatever example you are giving, it is kind of real-time example, real-time data processing. So I get the data, I has to process this in next few milliseconds or few nanoseconds. So usually the earlier, I would say the earlier version of Linux has not that capabilities of meeting that goal. That is why you find so much real-time operating system in the market. Nowadays, Linux is also competing in that area, still not overcoming others because it has too many modules, too many jobs in hand, too many tasks to do. Real-time operating system are very much simpler, dedicated to a particular job. It is not used to, Linux is there, you can watch YouTube, you can play games, you can chat with your friends, you can watch movies, you can then do some work. So it's a multitasking, multi-OS environment, right? But the real-time operating system are usually very dedicated. For example, in the automobile, in the car, there are some operating system running, and where say you are scanning any image. So it's an automobile industry where you are checking in your next 100 meters if there is any object or not. So whether there is a chance of accident or not. And if you are, so that means that is one of the examples that you are giving.
Exactly.
So the camera is getting the image, and then so that means the driver of the camera getting the image, which is running in the kernel space, and then it send it to the user space. The user space has to process the image, and based on that, it should instruct the driver or the engine, the ECU, that the car needs to be stopped right now. If there is a delay of 1 second, it's boom, right? So Linux or the scheduler may not be able to do that, but yes, from 2.6 kernel onward, the scheduler has been improved quite a lot. I work in the 2.4 kernel also. The scheduler was not as smart as it is now. In now in 4.4 or whatever, the scheduler is pretty much smart now. Still, it is not as the real-time operating system. So to answer your question, it all depends on the scheduler. In your example, scheduler plays a major role.
Yeah. Okay. All right. I think that the next question which I'll ask that might deviate, so we'll referring to.
No, you can ask. If it is really deviate, we can stop. No problem. You can ask.
Okay. So do you think any better mechanism to achieve such thing?
Yeah, that is definitely beyond this app. We can talk to you later. Okay.
Sure. Yeah. Thanks.
Tathagat, even in 2.6, right? There used to be the real-time scheduling for a user space process, right? There is
Yes,
FIFO and round robin.
actually, there is another version of Linux, RT Linux available currently. So some people are using RT Linux also in real-time environment. But I have been working on real-time operating system also other than the Linux, and I have seen that those are pretty much simple. And believe me, in many operating systems, there is no such user space and kernel space context. There's only one context. All are system context or kernel context. So there's no way of context switching between user space and kernel space. All the programs, those are running in the, say, kernel space. So definitely that has a huge advantage over the Linux. If I do not have the user space concept, then there is no point of having user space and kernel space context switching. So definitely I am one step ahead of the other system which have this.
I have a question. The two kernel process can communicate with each other through a network. Can you explain it in a little more details, like how it can happen over Netlink?
I'm not talking about the internal details. I will talk about that definitely, but not today. Suppose, okay, let me go to the next slide. Then you will get some idea. Then I will get back to your question. If I somehow forget, please remind me again. Okay, but I will give you the answer in the session as much as possible. Okay, please mute yourself if you do not have any question. Someone is still unmute. I am not sure who is that. Getting some noise from there. Maybe Maqsood Ahmed or Nagaraj. I'm not sure. If you have any question, please shoot. Otherwise, mute yourself. Oh, I guess. Okay. So now you have already understood that this is a full duplex communication. User can send the message, and we have already talked about this asynchronous part quite a lot. So yes, kernel can send the message back to users also. So this is a full duplex communication, unlike the RCTL and all that. The advantage of Netlink socket is that if you are familiar with the BSD socket, like socket call, bind call, connect call, listen call, receive, send, and all that, then developing or implementing the user space program using the Netlink socket is very much simple to you. Can you please mute Maqsood Ahmed? Yeah, thank you. No, noise is still. Anyway, so and in most of the cases, say you are using the existing features of kernel modules which are supporting the Netlink socket. That means in many of the cases, you do not need to develop your own kernel module. Say you want to set an IP address, you want to modify the route table, you want to check the firewall policy, and so on and so forth. Then those corresponding kernel modules are already supported in the kernel. You do not need to implement that. What you need to implement, you need to implement the corresponding user space application. So in summary, in most of the cases, your implementation is limited in the user space application. You do not need to very oftenly need to implement the corresponding kernel module. And on the other hand, if you are very much familiar with the socket APIs, and you have already developed TCP UDP socket and server client application, then definitely implementing a new solution or new user space program using the Netlink socket is a very straightforward job to you. We will talk about socket and bind API in today's session. So there we can check how it is easily mapped with the socket API knowledge we have for the other socket. Okay. Here is the protocol types that we are talking about. So yes, it can support multiple protocols. For example, here we have talked about Netlink route, Netlink firewall, Netlink RD. So these are the already supported protocol types. That means these are already defined in the netlink.h. So now someone was asking how we can add TCP UDP protocol type. Someone was asking earlier. Can you please repeat the question now?
Yes, I was asking that question. I got
Yes.
it. It is not about the transport. It is more about the what is the process doing. So it's defined
Yes,
based on
this
that.
is about the protocol type that is supported by the Netlink socket. This is not about the L4 layer protocol.
Got it now.
Yeah. So now you can add the Netlink. So if you want to, if you are interested in the routing table related information, you want to set or get it, then you must, while you creating the Netlink socket, you must specify the protocol type as Netlink route. If you are interested, on the other hand, on the firewall policy, you need to set or get firewall rules, then definitely the protocol type must be Netlink firewall. Similarly, if you are looking about the ARP table, modify the ARP table, get the status of the ARP table, then Netlink ARPD should be your protocol type. Here, you can add your own protocol type. So for that, netlink.h must have that number, say up to this, whatever existing protocol numbers are 1, 2, 3, 4, 5, say current last number is 78. So that means if you want to add your new protocol number, it has to be 79. But note that if you want to, and then you can implement your kernel module for that 79 protocol number, and similarly your Netlink socket application will use this 79 as the protocol type number, and then that user space program can communicate with the kernel module and share the information. But please note that if you want to use the same set of application, that means the user space program and the kernel module, to a different system, to a different Linux, then again you need to add that entry of the 79 protocol number in that machine's netlink.h header file. Please wait. Sorry for the interruption. So, so now this part is clear to you, I guess. Shall we proceed to the next slide, or you have any question?
Sir, if it's a Netlink route, so the user space will make an API call, the Netlink API call using the Netlink route number, and at the kernel side, how it will be routed to the kernel modules, like how it is done at the kernel side.
Your question is not clear.
Sir,
okay, let me give. Please wait for 2 more slides. I will show you how this Netlink route is specified. Then you may have some better idea, and then you can ask the question again. Okay.
Hey, this is Srinivas. But
Yes.
I think we have ethereal packet sniffers and other things. I mean, for the general socket calls and all. But
Yes.
if it is you going through Netlink, can we see what packets went while going through Samba and all? If your file system calls and your can and also the network device driver calls are, I mean, talking to each other. All these things, packets we will be able to get in the ethereal trace or
No, no.
no. So then, how do we debug if something goes
Uh,
wrong?
the user space is developed by you, and the kernel module is also developed by you. So you can put some print message or debug tool. There are multiple debug tools there, print K, GDB, KGDB. So you can use those tools to debug whether the message is getting sent or not properly, or what is the problem that you are not getting the expected result. But each tool or the Wireshark tool is running on the interface where the packet is going out or going in or coming in. So Wireshark will not capture those communication.
Okay. Also, one more question. In general, the IOPS will be there. I mean, whenever we are writing to the disk or something like that. So how does this Netlink improve the IOPS? I mean, it will be the same, right? So sometimes, disk is very, I mean,
Are you talking about the Samba example that I was talking about?
Yes.
No, I am just giving you one example. If you think that way the performance improvement will not be there, you may not use it. But my perspective was different. You are talking about the writing to the media is slow. If the writing to the media is slow, then you cannot improve that one, right? That is your question.
Right.
Yes, that you can definitely means that is already there. Means you cannot improve that. If the device driver is taking, say, I'm talking about some absurd value. Say it is taking 1 millisecond to write 500 byte or one block to the device driver. Then whether you are bypassing the kernel, the context switch or not, it will take that 1 second always, right?
Right.
You cannot improve that one. But on the other hand, see the overall performance from whenever you are writing any content in the node file, which is in my machine, you are getting the experience of whether it is slow or not. That depends on multiple factors. One, how much means what is the network speed between your machine and my machine? Point number one. Second is how fast my application is getting the data. Third is how fast my application is writing to the data. Then also there are two device driver. One is the network device driver, which is getting the data from your machine. So the performance will definitely depend on the performance of the network device driver. Similarly, whenever you are writing or reading data or reading blocks from your hard drive or say any other storage device, so the performance of that particular block device is also here. I cannot bypass this. But apart from the performance factor of network device driver, the block device driver, and all that, there is another two factors. One is the context switch from kernel to user when you are sending the data from from network socket. So your application is listening on a TCP socket, so it is getting the data from the network stack to the application, right? So there must be a context switch occurring between kernel and the user space.
Okay.
And that will definitely take some time, whether that's a millisecond or microsecond or whatever, but that will definitely take some time, some delta time.
Right.
Again, when you are sending the data or writing the data, say you are calling the write API. Okay,
right.
So that means again that data needs to be come from the user context to the kernel context. So again, one context switching will be there.
So context switching will be minimized if you
yes.
But is Netlink is chargeable, or is it you need to pay for it, or
No,
is it free?
it's coming free with Linux. If you have Linux, then you have that Netlink software. You don't need to install anything or pay anything to me or anyone else. It's not my problem.
Okay.
I'm just sharing my ideas and knowledges. That's all. Any more question?
No. Go ahead.
Thanks. So there are two. I'm just giving you two user space package example where one is using the Netlink socket, which is very much now recently used, and the other is if you are familiar with the Linux operating system for quite a long time, then you have you have used those tools also. So IP Route 2 is a set of is a package that provides multiple commands or tools. For example, IP, TC. TC stands for Traffic Control Management. Bridge. So if you want to add create any bridge device and put your physical interfaces under that bridge, that can be achieved through this bridge command, and internally that bridge will use the Netlink socket. So definitely you must understand that there is a corresponding kernel module which is providing this bridge protocol type support. Similarly, using the IP command, I will I will talk to the admin and get back to you whether we can share the slide or not.
Yeah, I know IP space here you are talking about, the command IP space here.
Right? Yeah, no, someone is asking whether we can share the slides here.
Oh, okay.
I will get back to you once we talk about with the admin. So yeah, so again, the IP is for the management of the networking table, network interface, and all that. These are also internally using the Netlink socket. TC is a very powerful tool. I'm not sure how much you have used it, but for the quality of service, for the traffic management, TC is heavily used. Not only in the Linux desktop or laptop environment, but it is more used in the router kind of device or network devices, embedded devices. TC is heavily used. So if you do not have much idea or you have never used that TC, I would recommend you to read the man page and do some trial error with this TC tool. These are lovely tools to get some knowledge. Now, on the other hand, there are some legacy tools. Very famous one is the Net tools. You may not know or may not hear about the Net tools, but I'm quite sure that you definitely know the name of ifconfig, arc, route, netstat. Your question is, can we get a sample program how to write and use Net? Yes, we will. Not today. Today we will not have the time. Looks like the slides we have, I have planned, we may not be able to cover that one. But yes, definitely we will cover that part also. Writing some sample program, not only in the user space, but in the kernel module also. We'll have our own kernel module through which user space program will communicate with the kernel. Now the net tools, yes, ifconfig, arc, route, netstat, these are the very famous command. You all know the ifconfig command is used to set and get IP address, MAC address, gateway, interface up, down, and all that. ARP is for maintaining the ARP table, not only maintaining the ARP table, but monitoring the ARP table. Route is similar to ARP, but ARP is for the ARP table, route is for the route table. Netstat is the network statistics, whatever connect means whatever existing connection are there, or which socket are listening on which port, which application are listening on which port, whether this is a TCP or UDP. Those sort of information you can get through the netstat command also. And internally, they are using RCT. So now let us check how this Netlink socket API is used. So we will talk about two APIs only today. One is the socket and the other is the bind. Then in our next class, we will go through the other APIs also. So the socket API, I have just stated the standard socket prototype. What is that? It is that it takes three arguments. One is the domain, the other is type, and the third is the protocol. So if we create the TCP socket, then we used to provide the domain name as AFINet or PFINet. The type is for the TCP is socket underscore stream. For the UDP is socket underscore dgram and all. And in the protocol feed for usually TCP and UDP, we specify the name. But say you are creating a raw socket, which is interested only for the ICMP packet, then you can specify the domain as AFINet, type is the sock raw, and the protocol could be ICMP, IP proto ICMP. So if you are familiar with these socket APIs, then creating a Netlink socket is a very easy job for you. So instead of AFINet, you need to mention the address family as the AF Netlink. That is the first difference between the other API, between the other socket call. The second argument has to be either raw or datagram, because Netlink is internally is a datagram kind of socket. So you cannot specify here the sock stream. So usually whatever code I have gone through, or even I have implemented some Netlink code also, we usually use this sock raw option. I do not know why sock raw is heavily used compared to sock datagram, but that is how it is. And now the protocol field, you can use the Netlink route, Netlink firewall, Netlink ARPD, and all that. So if you provide the protocol field as the Netlink's route, that means your program will communicate the kernel module, which is responsible for handling the route table. Someone has had question for that in our previous slide. Can you please repeat that question?
Yes, sir. I understood.
So it is clear now.
Yes, sir. So the sock raw and the sock dgram. So let's say it's a asynchronous. So sock dgram, it's a datagram based communication. Basically, it's a fire and forget, right? So it's a asynchronous one. So since the Netlink provides the asynchronous mechanism, so how the kernel module will notify a user space application using datagram?
So going back to your first statement, it is that send and forget, right?
Yeah.
So which one will forget? The sender. Correct? So suppose you and me are talking using a UDP connection. Okay. So if you are saying, hi, how are you? And you are sending this in 4 packet, hi, then how, then are, then you, then it may happen that the how is somehow getting dropped. And your machine will not repeat that how packet. Correct?
Right.
Now, but if my machine has received 4 packets, hi, how, are, and you, then those will never be dropped.
Right.
The basic difference between UDP and TCP is from the connection or from the network point of view, not from the socket queue point of view. If the socket queue, the receiving side socket queue get the packet, whether that's a TCP or UDP, if it is in the queue, then it will never be lost until and unless the socket queue is overflowed. That's a special case. We are not talking about that. But until and unless that, if the socket queue somehow get the packet, it will never be dropped.
Okay.
So the dropping can only be happen at the network connection level due to some network traffic or something like that, or your driver is not able to send, or my driver is not able to receive for some reason. That could be dropped. But here there is no such way because those two are running in my machine.
Right.
So network congestion is out of this case.
Right.
So getting the information dropped is I cannot say these are 100% assurance, but definitely you can assume that this is 100% assurance that it will not be dropped because physical network is not involved here. So network congestion and all that, those will not be involved here. So kernel module will definitely send the packet and it will be queued in the socket queue. Again, why I'm talking, I cannot assure you the 100% assurance. Again, the limitation of the resource. If the socket queue has a very limited resource, as I have been working in the embedded system, so I have a tendency of thinking about resource, very low resource and all that. But if you are talking about Linux PC, Linux laptop, then you do not need to bother about that. There is plenty of resource available. So in that case, Netlink buffer will not be dropped or somehow missed.
Okay.
You got the answer, right?
No.
Yeah. Anyone? No, I guess. Okay, so this is how you can create a Netlink socket. So again, like the TCP and UDP socket, this socket will return a unique socket descriptor, which you should use for further socket APIs like bind, send, receive, and all that. So that concept remains same. There is no change in that. Only change is the arguments of the APIs, for example, in the socket. So similarly, there are some change in the bind also. See, if you want to bind for a TCP socket, what you need to do, you need to fill up a structure, a socket address structure, where you need to fill up the IP address to which you are listening. It could be IP any from where, or any particular IP address of your interface and all that. Similarly, the port number, it is 21, 22, or any standard code or any user defined code, say 1, 2, 3, 4. So those kind of information need to be provided while you are calling the bind API for the TCP socket or the UDP socket. Similarly, in the Netlink also, the bind API is associated with a socket address. And again, compared to the socket address structure, we have a similar socket address underscore NL, that is Netlink. So you can easily remember that. And this structure has 4 members. One is the NL family, which has to be Netlink. The second argument is mainly for padding, so you can just set it as 0. That is just making the structure aligned so that the performance can be improved. The third is important point is the PID, so through which you can uniquely identify the socket number. And the third is for the NL group. So if you are interested in listening multicast group, then you can specify the multicast number. Each protocol type has 32 separate multicast group. This is a U32, so that means a 32 bit. So each one bit will represent one particular multicast group for each of the protocol. And if you are not talking about, if you are not interested in multicast group, if you are interested in unicast, then this NL group field has to be set as 0. So the NL PID is usually when you filling it up the structure, you usually set this NL PID with the process PID. So you call the get PID API, you get the PID number, and you can set that NL PID number. Again, it may happen that you have multiple netlinks separate from a single process, which have say multiple thread. Then you can say there is one example I can give you. You can just shift the PID to 16-bit, so one after another, and then you can assign it along with that. So that will make the NL PID field as unique. If you do not fill this, then bind will internally fill its own value. But I will recommend you to filling it up with your own PID. As I said, the NL groups 0 is for the multicast, and then you can call the bind API something like this. This is very much similar with the other bind calls. So here also we are calling, the only difference is the argument. It's not the argument type, the argument values. So that is more or less done for this topic. That was the last slide. So if you have any question, we can discuss.
Tadavata, sir, I have one question. So
Yes.
in case of that Samba example, right? There is no for example, for your PC, the communication will happen between the network driver and the file system driver. So
Yes.
so in the file system driver, what will be binding it to? There is no IP or anything, right?
This bind is for the user space application, right? This API is not available in the kernel side. So in the kernel, there will be different. I will talk about that in our next session. How two kernel modules can talk to each other.
Okay.
What are the APIs that you need to call?
Okay. Got it.
Yeah, I have a question here. So, yeah, so Netlink is a datagram oriented service, right?
Yes.
It supports SOAP raw and SOAP diagram. So, does it support SOAP stream as well?
No, as I said, SOAP stream is not supported.
So that means it only supports UDP traffic.
Yes.
Okay. So, what about the reliability? Like, so suppose
as I said, the reliability is between two remote machines. Here, it is communicating within that machine, so reliability is already there.
Okay. And one more thing, so we can also fetch the data from kernel using mmap. So would you like to put some
Sorry?
mmap.
Nmap.
mmap. You can also map the kernel.
Yeah. Memory map,
yes.
Right? Yeah. So yes. What is your question?
So I mean that is also a method we can fetch the data from kernel to user space. So can you also compare that with this Netlink and IoT?
No, that is not in this course.
Okay.
We are only covering the Netlink, and then later we will talk about Netfilter.
Okay, fine. Thank you.
So by default, this socket address will be directed to the kernel space, right? So
yes.
There is no such as destination. So it is by only the source is the process that is handling, and it will be directed to the kernel.
Correctly pointed out. So as you can see, means I was just expecting that question. I was just waiting for this question. So the basic difference between TCP UDP bind call and this bind call is that there is no port, there is no IP address. Instead of that, there is a PID and the group. So that means it is not able to send the packet or receive the packet from outside.
Okay. So by any intent, the process-to-process communication inside the same host cannot happen through Netlink.
Yes, two user space program
Space programs.
cannot communicate with each other using this net.
Okay. Yeah.
It is only between two. It is only between user space and kernel.
Yeah.
And between two kernel nodes.
Okay. Thank you.
So one end has to be kernel mode.
Yes.
Yes. Any more?
So
yes,
this Netlink thing, right? So mostly what I'm asking from the perspective of a router or a switch, right, which is a Linux based switch or router, right, where we have a like multiple thousands of routes, right, and all, right. So is it scale that well, this Netlink thing? It will go that good as a reliability and the scale wise, and
again what you are trying to achieve through this Netlink stuff means many of you are talking about the reliability. So let me just get the question properly. Means what do you mean by reliability here, or what do you want to achieve through this Netlink stuff?
Yeah, so what I'm trying to tell, right, suppose you have a routing protocol, right, which detect the change in the route, right. There is a change in the route, right. Now I have to change my around 50k routes in the kernel, right. So I'm talking about from the router perspective, right, not from the normal.
So you want to change your routing entry of your particular router, not the other router connected in the network, right?
No, but since it is a router, right, it has scale is very high for the entries, right. So how we keep on calling all these things, right, one by one, right, all replacing all these things, right. So I was just trying to understand.
No, you are just mixing up many things here.
Okay.
See, I'm just giving you some simple statement so that you can be easily understand. Say you have one Netlink application running in your router. The purpose of that application is to, whenever any change in the routing entry, it will get notified. Correct?
It's both way from the application also, right. Suppose there is a routing application running which is stalled route in the kernel, right. So that way also, both way.
Means you want to set something in the routing end.
Yes.
Yeah, you can set. So that will be an user demand process, or based on some event you want to add something dynamically.
Yes.
Correct. So that means one event is occurred at the kernel side, and one application is running in the user space. So that will get the notification from the kernel. That is step number one. Step number two is based on the event that you have received in the user space application, you may or may not add a particular entry, or rather than saying add, you may want to modify the routing table. Correct?
Yes.
So you may want to modify one single entry in the routing table, or you may want to modify multiple routing entry in the table, right?
Yeah, so I was talking about the multiple routing entries and with the scale, kind of a large scale, right? So,
yes. So that is the purpose of your application reliability. This is not the responsibility of a Netlink socket. Netlink socket is giving you the the knowledge that some event occurred. Point number one. Netlink socket, on the other hand, also giving you the provision of changing the routing table. Now, if you are changing 50k number of routing table at one shot and can do it properly, that is up to the application program and the current routing condition. That is not the Netlink's responsibility, right? If you send the information to the kernel module, then it will modify it. Even if you are using RFTL or all that, means why you are afraid of the reliability? If you are thinking of you will send the packet and the kernel module will not receive, if you are thinking about that reliability, no, there is no such problem with that reliability. If you send a message from the user application, kernel will definitely get that.
Yeah.
Similarly, if kernel
yeah.
get the notification, user space will definitely notify.
Yeah, so I was coming from that, right? If I return, suppose a number of Netlink, right, call and do a write, right, and then goes to the socket layer, right? Now, now suppose I did certain amount of write, right? Now it will other thing the next write, since there is no space in the socket layer, right? It may block the.
How can you overflow the socket layer without completing the first command? You cannot send 50 routing 50K or 50,000 routing table entry at one shot. You cannot do that, right? You need to do this in a loop.
Yeah, loop only.
So in the loop only, if you send the data one after another, say I'm talking about not 50K, I'm talking about 10 entries. So if you want to add 10, if you want to modify 10 entries in the routing table, you need to call that send API from the net using the Netlink socket 10 times.
Yes.
So that means every time you are calling the send API, that data will be queued in the socket. And definitely when again your user space application get the chance to send the next packet, the socket layer will definitely send the packet to the kernel module. That is why we are giving the scheduler there to run the application, so that there is, otherwise this if your operating system is not able to handle that situation, then how can you send the packet to your other machine? Say you are watching YouTube, or see as we are doing this session using network application, so you are talking something and that I am receiving properly. So that again, forget about Netlink, because the socket layer is same for Netlink, TCP and UDP. So in the TCP, you are talking something, or in the UDP you are talking something, and socket layer queuing that message, and you are talking very fast, or I am talking very fast. That means the socket queue is getting the data quite fast. It is the job of the socket layer to free up the memory so that whatever I am sending to the socket queue is not getting overflowed. That is a typical producer consumer problem that need to be taken care by the socket layer, and that is not related to particular Netlink. That is common for all the socket. You get my point?
So basically, I mean, when it is full, right, the upper thing will be blocked, right? The socket call will be blocked, and the reliability will be assured, right? Yeah.
Definitely. So send call is like the TCP or UDP is a blocking call. Here also send call will be blocking call. Okay, I guess this is done.
Is there a plan to update ifconfig or the R, which like code base, which basically uses older IOCTL to Netlink? Obviously, IOCTL will be there for the backward compatibility, but is there a plan to update that in the code base to use Netlink sockets instead?
For that we need to talk with Linus Torvald. I am not the guy to do that. Sorry. But I do not. Not joke, but yes. On a serious note, if as we already have the IP route to tools which is doing the same thing of the if config. That means they are not planning to upgrade the if config to replace the IOCTL or having both thing supporting IOCTL as well as the Netlink socket. Otherwise, they will not develop the IP route 2. They will instead upgrade the net tools. So, to my understanding, I think there's a very minimal chance of doing that.
Okay, that makes sense. Yeah.
Sir, and one more question. Let's say in the socket we have this server and the client. So server keeps waiting for the connections. So how that is like with that with that model, how can we relate it with the Netlink part? So
Netlink also you will call the receive message and will be blocked there. Wait for the event to be occurred.
So the receive call will be used by the kernel program as well as the user space. So both will be kind of receiving the messages.
Yes, in a way, yes, but kernel module will not the receive call. It will use a different function, but internally they will use the same thing.
Okay, so both will be kind of in listening state for the messages to come from the kernel and the user space to the kernel models.
Oh, I think I got your question wrong. But if you are talking about kernel to user, then the kernel module will wait for that event whenever you sending the message. So that will be again asynchronous. Similarly, the user space program will definitely wait for the receive message.
Okay.
To get the message from the kernel.
Okay, that's great. Thank you.
One question here. So Netlink sockets sometimes miss the message also. So
very rarely, but yes, it can.
Yeah. So is there any mechanism that we give the foolproof solution for the Netlink?
I use Netlink quite a lot, but I never see such case where Netlink miss the event.
Actually, what we've seen that IOCTL is preferred more when the message guarantee is concerned.
I do not think so. Otherwise, they will not. If the IOCTL is so much robust compared to Netlink, then people will not develop this. Netlink comes after IOCTL, so it's quite normal to think that whatever feature that IOCTL was providing, Netlink will definitely cover that. Otherwise, people see version upgrade. It's a kind of version upgrade in the IPC. So if the version upgrade does not provide anything more, and it should cover the basic part that IOCTL is already covered. Otherwise, people will not accept this. Means you will move from Windows 10 to Windows 12 only when Windows 12 will cover whatever feature you have in the Windows 10. Along with it will provide some additional features. If Windows 12 coming out that no, I will miss some key features of the Windows 10, and then I will provide some additional features, people will not accept. So I'm not sure if IOCTL is robust compared to the Netlink.
My question was because it is asynchronous. IOCTL is synchronous and Netlink is asynchronous.
That is the advantage. So we are making it as an advantage part, not an disadvantage part, because there is a socket queue. So if you are thinking means the only way that message get discarded again if the buffer is overflowed. Otherwise, if as there is no physical network involved here, so the packet drop will never happen. Both are running in the same system. Correct.
Okay, maybe because it's uses the datagram socket and the raw socket.
No. You all are afraid about the datagram, but datagram is only problematic if two physically separated machine communicating with each other. Here, two modules are running in a same program. One is the user space and the kernel space. So packet drop due to network congestion or due to other network hop is out of question. That will never happen. And by the way, UDP is not means yes, we learn about TCP is reliable, UDP is not reliable. It is not that case that UDP is totally bogus compared to TCP. Otherwise, UDP will never use. It is heavily used in some protocol like RTP, RSP, and all that.
Tathagata, just to
Yes.
I think what the I mean maybe the looking at a different perspective, right, from the kernel to user when the events are going, right, and when they queued into the socket buffer, right, in the socket layer, right, since it might be a limited capacity, right, so your user if your user process is not able to consume it, right, the buffer has to be some
Yes, that is always the case for any socket communication.
Yes, that for any correct. Not only the
So,
Netlink, yeah.
Yes, that is true for TCP socket, UDP socket. That is a classical problem of producer consumer.
Yes.
So here the kernel is the producer. It is producing the data and adding to the socket queue. If
Correct.
your user space application is not smart enough to consume the packet quickly, then yes, definitely there is a chance of missing the packet. But that is very rarely happen because the resource are quite high. The socket buffer is quite high. It's very rare that socket queue is overloaded and then you do not have any what should I say? You do not have any more buffer to queue any more packet.
Yeah. So the Netlink socket also have some kind of socket option to increase buffer size or something that we do for normal sockets, right?
I need to check that.
Yeah.
I need to check that.
Yeah, fine. Thank you.
Because one thing you must understand is that the number of packet that is coming in TCP or UDP is very, very large compared to what you are getting in the Netlink socket. Because you are either you are sending some packet, sending some request to the kernel that give me the IP address of the particular interface. So for that you will get the packet. So how many packets you will get? 1, 2, that is all. Compared to TCP, there are tons of packets in lakh or in crores packets are coming in TCP session or UDP session. So there is a point of the socket buffer getting overloaded or overflowed. But here, how many communication will happen? Very few. And it will be event based. So even if it is asynchronous, so how many events are occurring and on how many events you are interested? 10, 20, that's all. So that means 20 packet will come. And it is very hard to imagine that your application is not smart enough to consume 20 packets before the 21st packet arrived. Correct? So do not worry about the buffer overflow in the Netlink. You are all worried whenever you saw that it is a UDP, but believe me, you do not need to worry about it.
I think in the send and receive calls, you have an option to increase the size apart from the default.
Yes, you can, but in Netlink, it is rarely used. Means I have never used. And I'm quite satisfied with the Netlink performance.
No. Actually, it was the answer to the question which came.
Okay.
Where
Understood.
somebody was asking
Thanks.
if you can customize. Yeah.
Okay, then. See you in our next session. We'll continue from there.
Thank you, Tathagata.
Thank you.